Hello, this is Mrs. Huntley. This is lesson 16 of Module 4, the computation of the slope of a non-vertical line. You should be on page 21 of your module, and your essential question for this lesson is, how can I calculate slope? Examples 1, 2, and 3 on pages 20, 21 and 22 are kind of reminders of what we did yesterday, kind of building on the topic that we learned yesterday. And what we're going to do is identify some points and identify the slope between the points. Remember, we talked about yesterday that our slope is a ratio, and we use the variable m to describe slope, and we show it as a ratio of our rise over our run. So on this first example, I'm going to walk you through the first one. I'm going to just pick a couple of integer coordinates here, and we're going to calculate our rise and put it over our run. So when I talk about integer coordinates, that's just whole numbers where the diagonal line is crossing a coordinate that I could identify with in the coordinate plane. Like this particular one is going to be, my x comes first, so it'd be 2, 1, if I was identifying this first line with integer coordinates. Now, how is that different from this point here? This point is also a point on the line, but my x coordinate would not be a whole number. So it'd be very difficult for me to count slope using something other than an integer coordinate if I'm counting between the points on the diagonal line. That's why I want to identify some integer coordinates to count between. So if I'm using this first one at 2, 1, and I'm counting up here to this one that's at, what is that, 3, looks like 3, 6, I'm going to count by rise, 1, 2, 3, and put it over my run, which is just 1 unit. And that would be my slope of this line. Now 3 over 1, remember I told you anytime you see a fraction, that's actually a division problem, and with a ratio we can divide the numerator by the denominator, and if I divide 3 by 1, I'm just going to get the whole number 3. So it would be proper for me to say the slope of this line is 3. What I would like you to do right now is identify the slope of example 2 and example 3. I would like you to pause the video, and then once you have those slopes identified, you can turn the video back on. Okay, so example 1 we did together, and example 2, your rise is 2, your run is 1, 2 over 1. Again, if you do that division, you're going to get the whole number 2. If you use different points on the line, that's fine. You should have still come up with the same slope. And the last one, our rise is 2, our run is 3, so we would say our slope is 2/3. The question it's asking is, what is different about this line compared to the last 2 examples? So hopefully you recognize that the last 2 examples, we could actually perform the division and get a whole number, whereas this one is going to remain a fraction. I wouldn't want to do this division and have a repeating decimal or anything like that, because it's much easier to count the slope if it's in a fractional form. You know, having it be the 2 over the 3 versus if I had multiplied this out and gotten a repeating decimal or a decimal or mixed number, something like that. So I want to leave it a fraction unless it's going to be clean and give me a whole number. So based on what we learned in the last lesson, what do we know about unit rate of a problem and the slope? Unit rate and the slope are numbers describing the same thing. The unit rate is going to be one of the problems whose slope is a whole number, because unit rate is usually described as a number of something per 1 unit. Like, you know, the numbers of miles per 1 gallon of gas, or the distance run in 1 minute or 1 mile or 1 hour, something like that. And we'll get into that more as we get onto story problems. So let's take a look at, oops, I just lost my page. Here we go. Let's take a look at this next example. We're looking at example 2 a little bit more closely. So I'm actually going to color code. So if you have some colored pencils or some highlighters, you might want to grab those. And I'm going to just go through this example more in depth. Remember, I said it didn't really matter which points that you chose, and we're going to prove that right now. So I'm just going to make some dots where I know my line crosses integer coordinates. And then I'm going to create some slope triangles, meaning I'm going to just identify my rise and my run. So this very first one, my slope, is going to be that 2/1 that we talked about. So I'm going to switch colors here, and I'm just going to go from this point down here to the one up here. My rise is longer, my run is longer. Let's see, my rise is 1, 2, 3, 4. And my slope is 1, 2. And finally, I'm going to do it with green. And again, I'm going to come from way down here to up here. This rise, it's going to be 1, 2, 3, 4, 5, 6. And my run, 1, 2, 3. And last one, going up 8. And then running 4. I ran out of room, so we'll put it over here. Okay, so let's go ahead and do this division. If I got 2/1, that's easy. That's going to be 2. 4/2, ooh, that's easy. 4 divided by 2 is 2. 6 divided by 3, 2. And of course, 8 divided by 4 is 2. So again, just proving the point, it does not matter which points you choose on your graph, you're going to get the same slope. Slope is something that is constant. Similarly, the slope is going to be consistent. From the first point to the second point on this graph, I had 2/1. If I went from the second point to the third point, I'd have 2/1. Third point to the fourth point, again, 2/1. And fourth point to the fifth point, again, 2/1. So it's going to be consistent. That's how you can tell when you're graphing a line if you're graphing it properly. Because if all of a sudden the slope between the first point and the second point was 2/1, and then all of a sudden we had a 2/3 or something like that, we know that we wouldn't have a straight line anymore. So what do we notice about the ratio of the smaller slope triangle and the ratio of the larger slope triangle? Hopefully by now you've recognized that they are equal. And are the slope triangles in this diagram similar? Oh, similar triangles. Remember that from the last module, module 3, we talked about similar triangles. I shouldn't have added those black lines. Let me see if I can get those out of here so that we can talk about similar triangles and you can see it more clearly. Hang on a second. Okay, so if we're talking about similar triangles, we can prove that they are similar triangles by talking about their angle criterion. Hopefully you remember that. So I'm going to say yes, the triangles are similar triangles because I can prove it using the angle criterion. And what did that mean? That means if you've got two angles that are the same, your third angle of the same measure, your third angle is also going to be the same measure. So in all of these similar triangles, I've got all different size triangles here, but this angle is the same angle in all 4 of them. Then this one is going to be a right angle on all 4 of them, which means, of course, then this angle is going to have the same measure on all 4 of them. And our side lengths, hopefully you're recognizing that those are proportional, which again, it meets the criterion for similar triangles. So it comes back yet again. Okay, the next example is kind of a repeat of what we just did. So what I would like you to do, this is looking back at example 3, and again, creating the similar slope triangles. So if you would pause the video, go ahead and do that. What I can do is go ahead and help you identify some integer coordinates where it's crossing the coordinate plane and giving you whole numbers in case you're not recognizing where that's at. So again, go ahead and pause the video, create your similar slope triangles, and make sure that they're all the same between all the different points. Okay, so hopefully you drew your slope triangles similarly to how I did it. And your smallest one, you should have gotten slope of 2/3. Your next one up should have been 4/6, but again, if we reduce that fraction, if we divide both the numerator and the denominator by 2, we'll get 2/3, so they're the same. And of course, 6/9 is going to reduce to 2/3. We just multiply or divide the numerator and the denominator by 3. And the last one should have been 8/12. But again, if we reduce that fraction, we'll see that the slopes are identical in all 4 of our slope triangles. And again, if we check between each of the points, this one up 2, right 3, 2, right 3, up 2, right 3, we've got a stair step going up, and it's going to be consistent along that entire line. Okay, so next point, or next part of the lesson, they're asking us to select 2 points, any 2 points, and we're going to label them P and R. And we're going to identify the coordinates of P and R, because all of these points on here do have addresses. So the first one I'm going to do, just kind of picking random here, I'm going to identify the coordinates. So my X always comes first, and then my Y. So I'm going to name this one P and this one R. So for P, my X is -2. Here's 0, so I go to -2, and then up 1. And for R, I don't go right or left at all, so my X is 0, and I go up 5. So I've identified those integer coordinates. I'm going to just erase those dots because those were just for me to be able to count, so you could see what I was doing. So I do have lines on this graph, so I could easily count my slope between the one point and the other. And if I do that, oops, it helps if I do it with a line. I'm going to actually label this a Q. And I don't know if you remember, going back to one of our last lessons, we showed you a notation about the length of a line, and we showed it with the absolute value signs. So how Eureka wants me to teach you about slope is that the length of PQ divided by the length of QR is your slope. It's exactly what we've been doing. It's our rise, 1, 2, 3, 4. The length of PQ is 4. The length of QR is 2. So our slope is going to be 4 divided by 2, or 2. Let's move on to the next part, or the next page, and I'm actually going to skip this example. They show you how to use how to do the slope formula, and they show it with all letters, and I just find that very, very confusing. I think it would be very hard for you to follow. So we're going to actually skip that part of the lesson for now, and we're going to come down here where we have some numbers, and we're going to do the same thing, but we're just going to do it with numbers instead of the letters. So here we've got P, and here we have R, and they're saying P is at 1, 2, and R is at 6, 4. And they're giving us a Q here at 6, 2. So they're saying our slope is the absolute value, or the measure of QR divided by the measure of PQ. So we have to figure out what those measures are. Being that we don't have lines, we can't count them, so we can use the coordinates to help us out here. So the measure of QR is going to be the difference of our Y's. If you notice, the X's are the same, 6 and 6, but our Y's are different, 4 and 2. So what I could do is take the difference of those to figure out this length. So it'd be 4 minus 2, which is, I could write that even, 4 minus 2, which is 2. and put that over the difference here, which if you notice our y coordinates are the same here, so we have to subtract our x coordinates, which would be 6 minus 1. And that's going to be 5. So the slope of this line would be 2/5. And that is a fine way of figuring it out. However, I would like to show you a little bit of a shortcut. I'm actually going to give you the slope formula right now, which might be helpful, and then I'm going to show you something called the Larkin method. So the slope formula says slope is equal to the difference in your y's, so y2 minus y1 over the difference of your x's, x2 minus x1. We're putting the numerals on them just to remember that we have two different points and to keep them in order. So if we've got our P and our R, our first point, let's call this our first point, and this our second point. So in keeping with our formula, the y from our second point is 4. The y in our first point is 2. The x in our second point is 6. The x in our first point is 1. So we're going to get the same thing we did up top, but we're using the actual slope formula. So if you want to write down that slope formula, however it helps you to remember it. I actually think the next method that I show you is going to be the one that most of you are going to use. And we unofficially call it the Larkin method. I don't think that's what it's really called, but I believe it was Mrs. Hoekstra learned this from somebody who works at Larkin. And we draw an L. And we pretend that this L is like a wall that our numbers can't jump across. And we're going to have our X's on one side of the wall and our Y's on the other side of the wall. And they're going to straddle that wall. So our first point, our P was 1, 2. So we're going to put our X1 over there, our Y2 over there. Is that our point? Okay, and our other point was 6, 4. And we're going to subtract down. 2 minus 4 is going to be -2. 1 minus 6 is going to be -5. Now it just worked out that we have a negative over a negative, and hopefully you remember our integer rules. When you divide a negative by a negative, you actually get a positive. So this will be 2/5. It's the same. Whichever method you choose, you get the same answer. So this is just a way of calculating slope when you can't count slope. And there will be instances when you won't be able to count it, or when it won't be prudent to count it. Maybe it'd be too many different points. So let's go ahead and finish this up. On page 26, we've got a note to take. Translate the slope formula into words. The slope formula is basically taking the differences in your y's, putting it over the differences in your x. And that's how you figure out the slope. Remember, difference means subtraction. So we're not going to do the rest of the examples on this page, but what I would like you to take some time to do between now and class tomorrow is the summary on page 27. You actually have a diagram here that you can draw on and actually label up and summarize the lesson, the learning that we had today, and put it into your own words. And then we'll go over that tomorrow. So I hope you have a good night, and I'll see you in class.